Hello, welcome to Picture Me Coding. My name is Erik Aker, and my co-host is Mike Mole. Hello, Mike.
Hey there.
Mike, this week I have been listening to this musician whose name is Oneohtrix Point Never. Have you heard of this guy?
I have. I've not been entirely sure how to pronounce it.
I didn't know either. I found out that you can almost hear when I pronounce it. You can almost hear what it's like a mishearing of a radio station, Magic 106.7, Oneohtrix Point Never.
Yeah.
Um, he has this album out this year called Again, and I didn't expect to like it, but I really like it. I just like it fall into this hole, and it's just it's got this just it's so rich and bizarre sounding. It reminds me of Aphex Twin or other Warp Records stuff. He also has this album I really like from before called R+7, but that's like a 10 years old or something. Um, he's got this song that I sent to you, which is called Nightmare Paint. Got these just like totally deranged 80s guitar and drums and synth. It's very complex, challenging music, but I really like it. Did you try it out? Did you listen to it at all?
I listened to it once all the way through. I have yet to form an opinion, though.
It's one of those records that it kind of wants to shut the door a little bit, or maybe not shut the door, just close it. Like it's a challenging record,
It
but I
was
really like it.
surprising to me. I guess I had assumed that this was more of a sort of indie rock thing, and I didn't realize it was quite so experimental. I guess I
Yeah.
was expecting something more like, I don't know, the Dirty Projectors or something like that.
Did you ever listen? Well, he's also worked with The Weeknd and really famous. He worked with Rosalia. Did you ever listen to the Warp Record stuff? Aphex Twin, Square Pusher, who else? Wagon Christ. Who's the guy's name started with an A? Oh man, I should have looked that up.
Yeah, I've listened to Aphex Twin. Admittedly, not among my lifetime favorites, but
Oh man, Richard D. James album. That was a good one. What about you? What have you got this week?
mine is an album that one of my kids pointed me to. It's by a cellist named Ashley Bathgate,
Hmm.
and the title of the album is 8-Track. Has nothing to do, apparently, with the audio format of the 1970s that
Hmm.
I started listening to in my Ford Pinto back in the day. Um, so I think the name is taken from one of the pieces that's actually on this album. It's a Stephen Reich piece called Cello Counterpoint.
Oh, that sounds promising. I like Stephen Reich.
Yeah, this piece, I guess, was written. There are 8 cello parts, so it could conceivably be played by a cello octet if you could put together such a thing.
Or like an extended family of cellists.
Right? Yeah, if you had like the Von Trapp cellist family or something. But apparently, the way that it's frequently done is that there's one soloist and the other 7 parts are pre-recorded, and so the soloist plays with the pre-recorded parts. And so the other compositions on this album are sort of in the same mode, but by different composers. Very interesting stuff. Lots of variety, all sort of in that Stephen Reich minimalist vein.
I gotta hear it. I gotta hear that.
Pretty accessible too. And I found out quite by accident that it makes a perfect soundtrack for driving down a narrow country road at night in the rain. If you can manage to arrange that for yourself, it's an excellent soundtrack for that. So
I'm not normally doing that. I wonder if I could still enjoy this. I like that you said accessible. I kind of get a little suspicious of stuff that's in it, not so accessible. I had friends who loved later Coltrane, and they just were always talking about how it's the greatest stuff in the world. And I always felt like my aesthetic capacity is diminished. I just can't really appreciate this stuff or get into it. I love Giant Steps. I love My Favorite Things. I love A Love Supreme. you go off the 1965 deep end, and suddenly I just don't get it, and I feel bad.
Yeah.
I feel like I'm missing something. I want accessible. Is what I'm saying.
Eric Dolphy is that for me. I I just sort of stipulate that Eric Dolphy is a genius and that I don't get it, and going to move on with my life.
Okay, genius, and I don't get it. That's a good segue for what you wanted to do this week. So, Mike, your request this week was to talk about Leslie Lamport's work. And I like this idea, but I gotta say I don't feel qualified or up to the task. So I'm gonna, I will I will try to participate in this conversation. And I thought we should call this feature "Standing on the Shoulders of Giants" because Leslie Lamport, a giant in the field. Um, People call him the father of distributed systems theory. As you know, I tend to find distributed systems fascinating and um, like what's the word that they use in The Hobbit? Confusticating. I find them confusticating, and like they're hard problems for me to put down. I feel like I should be able to solve them, and they're frustrating. Why do you want to talk about Leslie Lamport?
Well, as you say, he is a giant in the field of distributed systems, also, very prominent computer scientist. I have this idea, which may or may not be true, that computer science being a young field doesn't really have famous computer scientists yet. Um, so
Wait, but I mean, Lamport's famous. Do you mean outside the field famous?
yeah, I mean, like,
Like if I'm at the grocery store, I could be like, I was reading this Lamport thing, and people in line would be like, "Oh yeah, he's amazing," like that.
like Einstein famous.
Hmm.
People don't understand relativity, but they know that Einstein was really smart, and
Hmm.
we don't have a Marie Curie or a Louis Pasteur or that kind of person. I guess the closest, as you pointed out, is Turing himself,
Yeah, he had a
who
movie. They had a movie made about Alan Turing.
right, and we named the key prize in the field after him.
Hmm.
Uh, but I guess my take on that is that the public knows, to the extent the public knows of him, it's because of his code breaking work during World War II, and less so because of his foundational contributions to computer science.
Turing, in this case, the Entscheidung's problem.
Yeah, and I think most working programmers have probably heard the term Turing machine or Turing complete
Turing
or things like that.
completeness. Yeah, that comes up a lot, right? Halting problem, right? It probably would say that.
Sure. So anyway, Turing I think is maybe as close as we get to our Einstein of the field, but I think of people who've been doing work in the era of digital computers is there really aren't that many people who are well known. There's some who have maybe a little bit of name recognition. Grace Hopper comes up occasionally.
Hmm.
Um, People like Marvin Minsky, maybe because of his contributions to artificial intelligence and things
Hmm.
like that. But
Hmm. Or Dijkstra's algorithm.
possibly, yeah. But I just don't think people outside of the field have heard of, these people who I think we identify with as being the real key people in our field.
Sorry,
So
we were still talking about outside the field. I was blending in my head like people I've worked with. Have you heard of these famous computer scientists?
yeah,
Lamport would be unfortunate because if people in our field who are just, journeyman developers like we are, hadn't heard of Lamport, because I think that we are confronted by the limitations and we sort of benefit from the things he dreamed up. Well, I would guess probably at least once a week. Is that an exaggeration? We're always dealing with systems talking to systems and failures that accrue as a result of that.
yeah, at least implicitly. I mean, it may be the case that people aren't thinking, uh, you know, that that's a violation of of an idea of Lamport's when they see a problem.
Hmm.
But anyway, I guess the bottom line being that I think we should do. I would like to do a series of these about prominent computer scientists, just to sort of, you know, give a little exposure to these
Okay, well,
important people.
you did me a solid by picking someone to start off with who I am in awe of, who I am a fan of their work, and I have read a few of their papers, and I know we have read them together and talked about them together. One thing I thought we could do today is talk about some of those papers. I haven't read all of them all the way through, but there's some famous ones that we could talk about. Um, there's also the famous joke that Lamport has, which is that a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. It's a joke, but it probably has some elements of truth. What do you think?
Oh yeah, absolutely. Well, I mean, we see this in sort of practical ways, not infrequently. Some third-party service that we're using breaks and causes havoc on our own system. So
Yeah,
it's
maybe
true in a sense.
people deploying stuff to the cloud. A computer you didn't even know existed breaks, and then you got to go to the business and say, "Sorry, the website's not working," and it's actually not my fault.
Right.
So here's the papers I thought we could cover, and then obviously there's a lot more in his career that would be worth talking about too. But the papers are these are the titles: "A New Solution of Dijkstra's Concurrent Programming Problem." That's the famous bakery algorithm. It was published in 1974. There's "Time Clocks and the Ordering of Events in a Distributed System." That's the famous Lamport Clocks paper, 1978. There's the Lamport-Chandy paper about distributed snapshots determining global states of distributed systems. That's 1985. And then, of course, the Paxos paper, which has my favorite title of his papers, The Part-Time Parliament. And that was
Yes.
actually published in 1998, but there's a little bit of a story on that one. I think we could talk about it when we get to it. But actually, let me pitch this to you. There's a quote I read of something that Lamport said in a Quanta magazine interview with him last year. He said, "Very few programmers think in terms of algorithms. When trying to write a concurrent system, if you just code it without having algorithms, there's no way that your program is not going to be full of bugs." I read this and I thought, is that really fair? What is he saying? What do you think about this quote?
I think it probably is fair. I think he's probably using a fairly rigorous definition of the term algorithm there. But, I would say that's probably true. We, even in the stuff that we're doing now, there are lots of situations where we do concurrency sort of informally, and it works well enough, and probably, could have benefited from some thought in a formal way, in the way he means it.
We're just kind of hacking stuff together. you can't, you can't. I think the reason why I find distributed systems so alluring is it seems like you could almost hack together a solution. And if you look at Lamport's career, when he talks about why he wrote a particular paper, it's almost always these people hacked together this thing, and I wanted to prove that what they were trying to do was impossible. So I invented a thing that does what they're trying to do. Oh, but by the way, I also proved that what they're trying to do is impossible.
There's an example from, I think it's from one of the TLA, learning TLA type courses, where they talk about a fairly simple example of you have a queue that you write to, you have a process that writes to a queue, and then you have a process that reads to a queue. And, we do this all the time. But one of the things they mention in that is, unless you specify it, what happens when uh, something reads from the queue before something writes to the queue? So, technically you need to specify what happens when you read from an empty queue. And that's not something that we typically think about when we're doing those things. But, just we're fortunate in that some of these things have sort of been baked in for us.
Mhm.
But, I think that's what he's talking about. And I think there are some cases, more complicated cases, where checking the model and trying to figure out what should be invariant are probably really crucially important.
Mm-hmm. I read these Lamport papers and I wish I could sort of put it in this mathematical box in the brain and see all the like routes in the maze. I'm mixing my metaphors a little bit here, but they sort of immediately, all the possibilities of what can happen immediately start going outwards. All right, let's talk about the bakery algorithm first. Have you looked at the bakery algorithm paper? A new solution of Dijkstra's concurrent programming problem, 1974. Have you ever read that paper? Do you recall that one?
I believe I did read it. I've also read the Dijkstra paper that precedes it, but
Hmm.
yeah, it's not as fresh in my mind as say the clocks paper.
Okay, well, we'll get to the clocks paper in a second, but here's the thing about the bakery algorithm. Lamport repeatedly talks about how simple it is. And the paper's short. I think it's only 7 pages. It's pretty readable. And the algorithm is only 8 lines. And every time I read it, I'm like, I have to look at it again and again. And he's got this bakery idea. There are customers entering the bakery, and then there are customers who are going to pick a number. Your number's higher than everybody who's picked a number before you. And then eventually you will be seen by the baker and you will get to do your critical section of work. So it's this like mutual exclusion algorithm. So it's kind of like while I'm entering, I'm going to choose a number. Okay, I got a number. Okay. While I am not being seen, I'm just going to sort of hang out in the background. Okay, now I'm being seen. For some reason, every time I look at the algorithm, I'm always like, this really works.
Yeah, I think Lamport had a bit of a tendency toward um, describing things as simple when in fact they were not simple for most human beings.
Yeah, that's my feel. I feel like he says this is simple. Should it be simple for me? It's going to take me a long time to even understand if this makes sense.
Well, there's obviously the famous case of nobody understanding the Paxos paper when it came out,
Yeah, well, we're going to talk about that one, I think.
but and I know there's a bit in the clocks paper where he talks about I think he talks about partial orderings and he says something about it. It's easy to show that this is a partial ordering, and again, it's one of those things where 2 hours later, after stepping through every word in there, I finally understand it. So
I cheated. I looked at a lecture and I was like, oh, okay, yeah, that totally makes sense.
yeah, I guess
um,
my comment is distributed systems are hard,
yeah.
and um, they were only simple for Leslie Lamport, which is why he's a genius.
I think they seem achievable to me. Like I feel like normal distribution of software engineering ability, I'm probably somewhere in the middle, right? And that's probably a fair assessment. I'm somewhere in the middle. And I still feel like I can work on distributed systems. I could do it. There's a quote again from the Quanta interview where Lamport says, and it strikes me about the bakery algorithm and him talking about how it's simple, but it also strikes me in relation to something you've said many times. He says you should write a description of what the program is supposed to do in such a way that someone can use it without having to look at the code. So he wants to be able to describe programs, and the code is just this detail like an implementation. It sounds similar to something you've said, where if people could cleanly describe what they want to achieve, actually building that thing in a reliable way is not the hard part.
I've probably adapted those things through osmosis from people like Fred Brooks and Lamport, so I can't take much credit for it. But yeah, I definitely do feel that way.
Let me give you one more quote this is from Lamport's personal site, which is pretty fun to read. He goes through every single one of his papers. There's like 150 lines of 150 references in there, papers or something, or maybe more. And every single one he talks about where it came from, the history of it, what he remembers about it, context around it. So this is about the bakery algorithm paper. He writes, For a couple of years after my discovery of the bakery algorithm, everything I learned about concurrency came from studying it. The bakery algorithm was also where I introduced the ideas of variables belonging to a process, that is, variables that could be read by multiple processes, but only written by a single process. And there's a side note there, like when I read that, and it's hard for me to imagine a moment before that was sort of expected and a possible thing, I guess. And let me just continue. He says, I was aware from the beginning that such algorithms had simple distributed implementations where the variable resides at the owning process and the other processes read it by sending messages to the owner. Thus, the bakery algorithm marked the beginning of my study of distributed algorithms. So, one thing I think is interesting about how he situates it here is he's not starting off with a whole bunch of different machines, right, which obviously don't have shared memory. He's starting off with separate processes. And like 1974 almost seems like, am I wrong in thinking that that seems like a pretty early moment in time to be thinking about this problem?
I would agree. I think one thing that's really interesting to me about Lamport's work in general is that he was doing it at this point in time where distributed computing was really very much in its infancy, and people were still trying to figure out what it meant. And what I find fascinating about what he did was he's entering this world where, okay, now you have potentially multiple processes uh, running concurrently. What does that mean? And he worked that out formally, and it turns out it's very, very significant.
Yeah.
you know, it's uh, it's almost surprising to me even now uh, how much different it is to go from one process to multiple processes.
To
It's still,
multiple machines, too. That's the other extension I find interesting, right? Machines communicating over a network, how it's sort of subtly related.
yeah. Although I think I guess in Lamport's time, I guess that wasn't that big of a leap. I
Hmm.
mean, there weren't. This may be totally ignorant, but I think we think of concurrency as being sort of uh, normal now because we have these processors that have dozens of cores. But I think at the time, um, concurrency was a little bit of a different thing. You
Hmm.
probably were talking about having processes on different machines, or you were thinking about time sharing systems.
Oh, okay. That's actually a good point. That this context is hard for me to imagine. So next, I want to talk about the clocks paper. The title is "Time Clocks and the Ordering of Events in a Distributed System," published in 1978. I don't know if you had read this before I said I want to read this paper, and I wanted you to read it with me, and we could talk about it. This is absolutely one of the best papers I've ever read. I just loved this paper. I struggled to understand it, but I loved this paper. Had you read it before we read it together?
I do not think I had, no.
Had you ever seen Lamport diagrams, those space-time diagrams before?
Yeah, I'd seen those, and I was sort of vaguely aware of what Lamport had done. Uh, he won the Turing Prize, and uh, I knew his name from that and his work from that. So, I knew this paper existed, just had not read it in detail until we started going through it.
I had heard of Lamport clocks before this paper, but didn't
Right.
really understand what they were. And actually, the first place I ever encountered Lamport clocks was randomly reading the code for a Python library called Celery, which is a distributed task runner library. It's pretty popular in the Celery world, and they do have somewhere in their code base Lamport clock as a variable. And I saw that at the time. This is many years ago, and I thought, wow, they must be doing something very heavy right here.
And they were.
They are, yeah. I'm not trying to diminish what they're doing. They're doing some heavy stuff. When I read the time clocks paper, It took me a while to understand the various pieces of it, and there are parts I think I still struggle to understand. But the basic idea that you can create a logical clock, not a wall clock, not a monotonic clock, but a logical clock. You started at 0, and every time an event happens, you send a message or receive a message, you increment that clock by 1. Whenever you receive a message, you compare the incoming clocks, the clock on the message, Lamport clock. And if it's greater than the value you know of as a process, you just take the max and then increment it. And over time, these clocks can help you know what happened before. And even that this relationship of happened before is an important relationship to be able to establish in a distributed system. My reaction to reading this was, wow, that makes so much sense. And now that you've pointed it out, it feels so obvious, but I could never in a million years have figured it out on my own.
I probably could not have either. I I think what I like about this paper is there's so many sort of very fundamental things that seem obvious when he says them, but only in retrospect for me. So, for instance, there's a relatively, sort of a throwaway line in the early part of the paper where he talks about how you can sort of define a process as something where uh, the events are all have a natural total order. So, a process is basically something where the events all happen in a particular order, and there's no concern about what happened first or what caused what. And I think about that fairly frequently in terms of trying to come to grips with the different types of concurrency we see. So there's there's just the fact that he's defining these events in terms of partial orderings and establishing a total order on the events across all of the processes is just such a appealing idea, that makes sense of distributed systems in general for me.
I think it's a radical, brilliant insight, and once I see it, it does feel obvious, like you said. But it was not obvious. It would never have been obvious until it was pointed out to me. And for evidence of that, the extensions that people layered onto it later on, like vector clocks, a dozen years later, or I guess they're matrix clocks now. I don't really know how those work, but matrix clocks is another extension on these things. Never would have occurred to me either. I like reading a paper like that where you can grasp the value, the meaning, the idea behind it, and it feels obvious. It feels true. I wonder
Just
though.
to
Go ahead.
just to forewarn people who may read this paper and expect it to be um, straightforward, I should caution that on the second or third page of this paper, he invokes special relativity. So
Yeah, what did you think about that when he started talking? Apparently, he did. So he did his PhD in mathematics, and he wanted to do physics, mathematics for physics. I think was his original intention.
I think this is one of those cases again where things that were straightforward to Lamport may not turn out to be so for other people. But I just love that line. It's something on the lines of, you know, this will sound very familiar if you know certain formulations of special relativity.
Yeah, I think I got lost over that. Yeah.
And you're like, okay,
Yeah,
well,
got it. I mean, I have to admit, I would not want to pretend that I read it once and immediately grasped it. It took work to understand what's going on in the paper, but it was worth it. It was worth it. I
yeah, I still have struggle with the sections at the end about physical clocks, but
Me too. Yes, I get stuck on those too. Yeah. I want to talk about time though. My mind starts connecting to things that I read as a student in philosophy, and maybe these are bad connections, but I sort of build this idea that time is a hard thing to talk about. And being a hard thing to talk about, it leads us into errors. We're sort of bewitched by our expectations around it. Maybe this is a terrible connection, but I immediately think back to the Critique of Pure Reason, Immanuel Kant. And he's talking about how space and time are these, I'm not going to do a great job, but they're a priori. He uses the word intuitions, which I really should not bring that up because I couldn't really give you this philosophical definition of it. This is a long time ago. But somehow space and time are foundational to every other idea that we have. I remember reading many years ago that time is only a thing we can perceive internally, and space is only a thing we can perceive externally. Similarly, there was this poem that I read probably 15 years ago, which kind of brings up a lot of this like philosophical tradition of time and struggling with time. It's by a poet named Robert Hass. The poem's called Regalia for a Black Hat Dancer, comes from his book called Sun Under Wood. Now, this might be a distraction. I apologize if it is, but it seemed connected in my head to talking about time. He writes, there was a time when, in the universities, everyone was reading Derrida, who'd set out to write a dissertation about time. He read Heidegger, Husserl, Kant, Augustine, and found that there was no place to stand from which to talk about it. There was no ground. It was language, the scandal of nothingness. Now, that may be a little too lofty and weird, but in my mind, it's connected that the time it's really frustratingly hard to perceive in the way that we normally perceive variables or aspects of our software as things that can cause us problems. Maybe am I out in crazy land here?
You're on the fringes of crazy land, maybe.
Okay,
But
all right. Can you
the
bring me back in?
I think there's some relevance here. I think one thing that we should probably point out about the clocks paper is that one of the key elements is that you have the sequence of events, and what you really want to know is what happened before something else. And of course, concurrency is the situation where two things are effectively happening at the same time. But so, this is where the partial ordering comes in, because with concurrent events, you can't really compare them as one happening before the other. They're concurrent.
Right,
But
absolutely. Let me one little detail. If you do not have a happens before relationship, those two things are just concurrent. And they, in like real time, they could be wildly different times. We just call them concurrent because we can't establish happens before. Go ahead.
right, I mean, it's not just that it's just not that it's physically impossible to do. It's that they're literally not comparable. You can't really uh, mathematically say one is before the other. Anyway, um, so I think one of the key things in the paper is that you can't simply use physical clocks to establish the happens before, which is the whole point of logical clocks. And I think part of that is because it's difficult to find clocks that it's difficult to synchronize clocks down to the time steps you need in distributed systems. But also, he does go into elements of relativity, and how difficult it is to really establish what it means for one event to precede another event.
Mm-hmm.
So,
And relativity matters maybe because, and this is a question, you don't have a static global like God observer of real time. Is that's what relativity is? That's the connection, right?
yeah, I mean, if you read I obviously am not an expert on relativity, but if you read stuff on special relativity, they use this term frame of reference.
Mhm.
And so, the, the, the way an event is perceived will depend on your inertial frame of reference. And so, um, again, we're sort of getting away from things we know stuff about.
Yeah,
But
definitely in my case. Yeah, I'm trying to ask questions, not sound like I have the
but
answers.
but I guess the thing I want to nail down here is that the whole point of logical clocks is based on the idea that it's difficult to use physical clocks to establish uh, the causal order of things.
Yeah, I mean, there's examples of major outages and bugs from systems trying to use physical clocks. I have a link to Cloudflare. They had this massive DNS failure because they were calculating two intervals in time, and at one point it went negative and it crashed a bunch of stuff.
Right. Yeah. The incorrect assumption that time won't move backwards.
It doesn't move backwards, exactly. I think the inability to use wall clock time too shows up in the distributed snapshots paper, determining global states of distributed systems. That's 1985. And the thing that fascinates me about this paper is he goes from 1978. He's got Lamport clocks. Of course, he didn't call them Lamport clocks, but he's got these logical clocks, and he's talking about happens before. It's like when I read that, I think, oh wow, that is interesting, an interesting relationship that you're building out. And then in 1985, he's like, well, it's going to be important to be able to snapshot distributed systems. I would never, ever have anticipated in 1985 that that it would be a useful thing to be able to snapshot the state of a system. Like, it just seems like it's like he sees into the future, these problems that we would have.
In preparation for this, I was sort of looking through history of distributed systems and came across a couple of things, and I got that same sense is that he's really formalizing things that have not been around for very long,
Hmm.
right? That are not even well established. So, like the clocks paper came out in '78, and um, if you look at what people were doing in terms of actual distributed systems in 1978, it was still pretty experimental. They were doing work at places like BBN and uh, uh, some of the universities, MIT. A lot of it was just sort of, hey, we have these computers and we have this primitive network. Let's see what happens if we do this type of thing. And so, the people doing practical computer science at that time were still really trying to figure out what the issues were and what was possible with the hardware and networks of the day. And so it's impressive to me, at least uh, from our vantage point 40 years later, that he was able to sort of anticipate and formalize these things at the point when he did.
I think you're totally right. It is impressive. I think the snapshots paper is fascinating because it's also a rejection of this idea that you're going to be able to rely on wall clock time. If you have a bunch of distributed processes, you can't tell them, hey, at 4 o'clock, take a snapshot, because you're never going to get what you think you're getting. You're never going to get some sort of consistent view of the thing. There's a really nice metaphor that shows up in that paper. I'm going to read it to you. I know we talked about it, I think, when we read this paper. This is Chandy and Lamport. They write, the state detection algorithm plays the role of a group of photographers observing a panoramic dynamic scene, such as a sky filled with migrating birds, a scene so vast that it cannot be captured by a single photograph. The photographers must take several snapshots and piece the snapshots together to form the picture of the overall scene. The snapshots cannot all be taken at precisely the same instant because of synchronization problems. Furthermore, the photographers should not disturb the process that is being photographed. For instance, they cannot get all the birds in the heavens to remain motionless while the photographs are taken. Yet the composite picture should be meaningful. The problem before us is to define, quote, meaningful, end quote, and then to determine how the photographs should be taken. What a great metaphor.
Yeah, I think maybe Lamport had some frustrated literary ambitions.
Yeah. Well, he says someone asked him. Actually, this is in the Quanta article. The question was something like, "Do you find beauty in code? What do you find beautiful?" And I don't know. When I read the Time Clocks paper, there's I don't know if I would have used the word beauty or elegance, but there is something once you grasp it that feels really simple. I started 0. I increment by 1. He said, I don't think in terms of aesthetics. I probably have the kinds of feelings that other people do, but I just use different words to express them. Being beautiful is not something I would say about an algorithm, but simplicity is something that I value highly.
I I like that quote a lot. It resonates with me, but I also wonder if simplicity means the same thing to him as it does to me. So
Absolutely. The distributed snapshots paper, dense, very dense from my perspective.
I know we haven't reached it yet, but I've read the Paxos paper a couple
That's
of
the next
times
one I want to
now.
talk about. Let's talk about that one. Part-time Parliament. Great title. So, what were you going to say about Paxos? Let's talk about Paxos.
So I guess we should preface it by saying that Paxos is effectively a consensus algorithm.
Yes,
And
and is this a good point for me to say I don't know how to do it? I don't understand it. I'm
I
like the
think
poster child for that point in the Raft paper where they say you teach people this and they don't get it.
I think that's fair. I think also, we should probably define what we mean by consensus.
Okay.
Do you want to take a stab at that, or you want me to
No, I
try?
would be my guest.
So I guess here the way I think about it is you have, a series of servers with uh, uh, certain state on them, and you're trying to reach a point where they all agree on what the state should be.
Hmm.
In other words, they're trying to reach consensus.
Hmm.
And this is a particular type of consensus. So this is in contrast to, say, Byzantine consensus, where you're sort of trusting that the systems in this type of consensus may fail, but they will probably not lie to you.
Right, right. So there's two types of Byzantine failures that I normally hear about. Maybe there are more, but the Byzantine failures I normally hear about are one, you don't actually trust one or more of the processes in your group. Two, you may receive messages which are corrupted. So these are not the types of failures we're talking about. You can trust everybody in your group, and if you get a message, it's going to be a complete uncorrupted thing.
So I read something that said that, or Lamport had said that he was trying to write a paper that was using a metaphor similar to the Byzantine generals problem, which is often used to describe Byzantine consensus. Um, and so he wrote this paper about his Paxos consensus algorithm based on this parliament in I guess it's an island called Paxos.
Yeah, Greece, yeah, Greek island,
And
ancient Greek island. What he says.
right, so he essentially describes the consensus algorithm through the operations of this parliament, and there are certain characteristics of this parliament that are unusual. The the members of the parliament may leave
Right, they
and
wander
enter.
in and out of the
Yeah,
Parliament
they
House.
wander in and out of the parliament house.
They write down their decrees in indelible ink. Actually, I really like the Paxos paper. I've never finished it. I have to admit that. But I like reading it because I could sort of, like, I enjoy the humor and the scene that he's depicting, this narrative, this weird
Right.
fiction that exists.
I like the attempt a lot. I just don't think it succeeded, and I don't think it's unfair to say that, because I think a lot of people who are far smarter than me also don't think it succeeded.
Well, let's actually see what he said. So, if you go to his website, he describes the whole history of the paper, and it's pretty funny. He first submitted it in 1990. He says, I submitted the paper to ACM transactions on computer systems in 1990, all three referees said the paper was mildly interesting, though not very important, but that all the Paxos stuff had to be removed. I was quite annoyed at how humorless everyone working in the field seemed to be, so I did nothing with the paper. A number of years later, a couple people at SRC needed algorithms for distributed systems they were building, and Paxos provided just what they needed. I gave them the paper to read. They had no problem with it. And then there were other people. There was like this history. And then finally, since 1990, and then finally in 1998, he's like, oh, I guess I should publish that thing again or try to. And so then they got it published. And they went back and they did this like joke about how it had fallen behind the filing cabinet and how it was
Right.
about this like ancient
Yeah.
civilization. It's a weird paper.
Yeah, it's very weird. It has this sort of like Borges Umberto Eco feel to it. Like,
Magical realism kind of thing.
yeah, sort of like, Slan Ukbar Orbius Tertius sorts of things. But
Yeah.
yeah, and he wrote a later paper called Paxos Made Simple,
Right.
because people didn't understand the original paper very well.
Well, actually, he writes, so listen to this. He says, writing about a lost civilization allowed me to eliminate uninteresting details and indicate generalizations by saying that some details of the parliamentary protocol had been lost. To carry the image further, I had never heard this. I gave a few lectures in the persona of an Indiana Jones style archaeologist, replete with a Stetson hat and hip flask. My attempt at inserting some humor into the subject was a dismal failure. People who attended my lecture remembered Indiana Jones, but not the algorithm. People reading the paper apparently got so distracted by the Greek parable that they didn't understand the algorithm. And I'm going to tell you, I like the paper. I have never finished it. I still do not understand the algorithm.
Yeah, he seems like a super fun guy, though. I'd really like to get drunk with him someday.
Oh, you know who he reminds me of? He reminds me of our family friend, Paul Dayton. Paul Dayton he's a marine biologist, pretty well known in the field of marine biology. He is a family friend of ours. He once co-authored a paper with his pig, whose name is Frances Bacon. And he would sign the paper and have put her paw print in the ink and then have her sign it too. And he would give out signed copies, and that was one of his most cited papers. But let me give you this passage that I like from the Paxos paper, which I think illustrates the style of writing. In modern parliaments, the passing of decrees is hindered by disagreement among legislators. This was not the case in Paxos, where an atmosphere of mutual trust prevailed. Paxon legislators were willing to pass any decree that was proposed. However, their peripatetic propensity can't even say it. However, their peripatetic propensity posed a problem.
Yeah, again, I think he really wanted to be a writer.
That's hilarious. Their peripatetic propensity. It's challenging for me to speak out loud. I mean, they're wandering in and out of their law house.
It's a beautiful bit of alliteration, though.
Do you feel like you feel like you really grasp Paxos?
No.
Okay, so I'm not in, I don't have to feel bad that I'm not the only one in this call who doesn't really get it.
No, and I don't think that's out of the ordinary. Obviously, Raft has largely supplanted Paxos at this point, as far as I can tell. And Raft far better than I do, but I think even after Lamport attempted to simplify the explanation, people were still sort of longing for something simpler, which was Raft.
Yeah, I guess I feel justified when I read the Raft paper. They do say at the beginning, "Hey, the reason we're writing this is Paxos is pretty hard." Like,
Right.
okay, I guess I feel better then. I guess they use Paxos at Google, though. That's what I have heard, that it's foundational to a lot of systems at Google.
Yeah, I think it's still probably widely used, or widely in the realm of distributed systems. I just get the feeling that Raft has largely replaced it for newer things, things that are being developed now.
I think the other highlights I would give, if somebody at work said, "Hey, what do you know about Leslie Lamport?" I would probably have to reference LaTeX, which I never use, and TLA Plus, which I have to admit I've always wanted to learn to use. I can kind of read it. I've always wanted to use TLA Plus. Do you have any comments about LaTeX? I have really no comments about it.
I don't have, excuse me, I don't have a lot of comments about it. I will say that it is very important to both of my kids who wrote most of their papers using it.
So they're publishing academic research and they're using LaTeX.
Yeah, I think if you're doing academic research and it involves significant amounts of mathematics, it's almost a requirement.
It's kind of surprising that Lamport shows up there, though, isn't it?
Yeah, I guess. I guess it's kind of like another famous name who's not known as well as he probably should be. Knuth did all this work on fonts, for instance, and it's certainly not what he's most known for in the computer science world. But I think it's just people get these itches to do things to make their lives easier, and so. But anyway, yeah, I don't have much to say about it. I have used it, and then that there's sort of ancillary bits of it that come up in using things like IPython notebooks. But I think you have to be more of a mathematician to really get the full flavor of it.
Okay, so I'm probably not in the audience for being able to really appreciate it. But finally, TLA Plus. TLA Plus is this thing that I have been exposed to a number of times, and I kind of look at longingly. And you might say, well, why don't you just use it? And it's because most of the time at work, it's this sort of side thing. I'd have to sort of justify, like, I'm going to spend some time really learning to write is it a proof or an exercise? I don't know how to think of it. Is TLA Plus a proof? It doesn't, I mean, it's not formally proving things, or does it?
I think it falls more into the class of what they call model checkers.
Model checker, right. That's the term I was looking for. Sorry. Yeah, you're totally right. Model checker. What do you think? Have you have you used TLA Plus?
Not in anger, no. It's another one of those things that like you, I try to teach myself about every 6 months, and then some work or life thing intervenes. But I think I'm getting a little bit closer now.
It's the parameters of these systems that we build where we have different services talking to each other and things happening over time. There are too many for my brain to hold. There's maybe a pop psychology observation that the human brain can hold 7 things at most at one time. I think this is why I find distributed systems so fascinating, because they immediately turn the volume up to 11 on how many things can you hold in your mind at once. It's like, you want to play that game? Let's solve these types of problems. The TLA Plus seems like a way of wrangling the madness. You specify your distributed algorithm in the TLA Plus language, and then you run an evaluator, and it exhaustively checks for failing conditions. I really want it, but yeah, I haven't made a real strong attempt to start using it.
There are cases in my current work where I know that a formal specification would help, but they are not the sorts of situations where when these error occurs, an airplane's going to fall out of the sky or something.
It's hard to justify the cost, maybe. Is that what you're saying?
Yeah, if you see something that happens twice a week and it's not affecting mission critical operations, it's hard to justify the time you would have to spend on this. But clearly, there are problems out there where it is justified, and I think this from what I have seen, this has become a more and more common tool, especially in big companies, your Amazons and Metas and places like that.
I'm excited to hear that it's a more common tool. I want to use it. I think people should use it. I wanted to bring up a quote that I'm not sure where I read this, but he was talking about the origins of TLA Plus. He said in the 1970s, when people were reasoning about programs, they were proving properties of the program itself, stated in terms of programming languages. Then people realized that they should really be stating what the program's supposed to accomplish first, the program's behaviors. I like this. I like this idea of we will describe the behavior of the program and then we'll evaluate those behaviors and see if they produce the outcomes that are acceptable, that are they don't violate, these terms that come up we've talked about in other papers. They don't violate our safety properties that we're trying to achieve. They don't violate liveness properties that we're trying to achieve. It strikes me similar in kinship. There's some kinship to a thing that I've heard you say many, many times. We're not good at describing what we want our programs to do. We seem to be pretty good at just sitting down and coding them up.
Yeah, and I think the the problem with both of those things, describing what they should do and coding them up, is that the the things you miss in describing them are often very subtle things.
Mm.
I think this is where stuff like TLA plus comes in to play. Um, I think the reason why like document based specifications, sort of writing down requirements only gets you so far is because of because of the edge cases you don't think about. And I think this is what model checkers find for you. Um, I don't think it, I think people have this impression of you have to write a perfect specification
Hmm.
before you can do coding. And I think with things like TLA plus and especially, what's it called? Plus Cal, the sort
Mm.
of
Hmm.
language that compiles into TLA plus.
Right.
I think you can sort of do this iteratively. You can sort of start out with a basic idea and then run the model checker and see where your assumptions are wrong and refine that. But yeah, I don't know. I have this sort of crackpot idea that more formal specification languages like this will eventually become popular because there'll be something you can hand over to a artificial intelligence to actually write code for you.
Oh, wow. Well, that's an interesting observation. I hope you're right that they become more popular. When you were speaking, it rung a bell in my head. It rhymed with, say, property checking, like property based tests, sorry, like quick check in Haskell, where you can assert properties about an application and then quick check will generate a huge variety of random inputs in order to validate that your properties hold, that your assumptions about the program hold. It sounds like a similar type of effort.
I think that's, in a sense, what model checkers are trying to do. I think what this adds to that is, the specification of invariance, so that the model checker can say to you, not simply, that this gave me a wrong output, but that this this violates this invariant. So if you don't change this algorithm, you're going to see bugs.
There's a property that you would like to achieve, and it is an invariant, it is being violated. That's what you're saying.
Yeah.
So someone asked him why TLA Plus hadn't taken off yet, and Lamport said basically, programmers and many, if not most, computer scientists are terrified by math. So it's a tough sell. And I thought, wow, they are. I'm kind of terrified by math, but other people are too. But I guess I don't look at TLA Plus and think, oh, this is math. It looks kind of Haskell-ish to me, maybe. But Haskell's, I guess, kind of math if you look at it in a certain way.
I think it's math. I, it's obviously not differential equations, but um, I think it's at least mathematical logic, and
Hmm.
um, I don't know that I agree with them that all programmers are terrified of it. I think there's what I hear is this is not worth the time because doing it the informal way gets us far enough
Hmm.
in most cases.
Well, that's exactly the second quote that I had from him. He had two reasons why TLA Plus hasn't taken off yet. The first one is people terrified by math. The second one is exactly what you just said. He said, secondly, every project has to be in a rush, be done in a rush. There's an old saying, there's never time to do it right. There's always time to do it over. This is a similar conversation we had recently. Because TLA Plus involves upfront effort, you're adding a new step in the development process, and that's also a hard sell. That sounds like exactly what you just said.
Yeah, and I very likely just stole that from having read that at some point in the past. Um, I've heard this from other people, even in our current job, that formal methods in general are kind of a dead end because no real programmer is ever going to do that stuff.
Yeah. I mean, that's similar to the resistance I had with Haskell, where I was arguing, oh, you can be a lot more assured that your applications will be correct if you learn this language and you jump through these hoops. And people said, I don't want to jump through the hoops. I'll just keep hacking it. It gets me 90% of the way there. It's working. And I've already got more tickets. So get off my back.
Exactly.
There's one final quote that I had for you, which is something that it rung a bell also with something you had said, where he said, this is just a general comment that I thought, whoa, that sounds just like something Mike said. He said, the world changes. If you build a program and it's really used a lot, you're going to want to modify it at some point. In the real world, you're not going to go back and start from scratch and redo everything. You're going to start patching it. And we've seen that happen. And as it goes on, the program gets harder and harder to deal with, harder and harder to modify. And eventually the code is either going to be thrown away or it's going to be rewritten from scratch. You know, entropy, that's a law. And then so you start patching things, it gets sloppy. But if you don't do this design right from the beginning, then every piece of the code you write is a patch. And you start out from day one with a mess. I love this quote of Eisenhower, who said, no battle was ever won according to plan, but no battle was ever won without one.
I feel that way too, and I always wonder how much of it is because I'm an old guy uh, and started off in the industry when that was more of a thing.
The
But
waterfall, like upfront design type of thing, is that what you're referring to?
yeah, I mean, obviously we were writing documents, not formal specifications. But there's another quote. I think this is a Lamport quote, and I'm paraphrasing it because I don't know the uh, exact thing, but it's something to the effect of just because you don't have a requirements document doesn't mean you don't have requirements. And you know, I think the modern response to that is, well, we do agile, and the requirements change so frequently, and they're captured in our backlog, and so on
Hmm.
and so forth. And
Hmm.
um, I I don't really agree with that, and I think it's probably a generational thing. I don't know.
I think we can at least listen to Lamport. It's not going to work if you're doing distributed system stuff. You can't just hack it together. You have to think about what you're doing.
That is fair. Yeah.
I really liked his call out to entropy because you raised entropy a few weeks ago. And I have honestly been thinking about your comment about entropy in software applications ever since. And you said at the time, maybe I'm using this wrong. I don't remember exactly how you said it, but you said, I'm not a physicist, so maybe it's unfair for me to use the word entropy. Here's Lamport. Guy studied mathematics and physics, and he's saying it's entropy. He's saying exactly what you said. I feel like, wow, this really gives philosophical cover to Mike's point. There is entropy at work in our software applications. They will turn to mud over time.
Yeah, I worry a little bit when people make entropy metaphors because there are real concepts of entropy in both thermodynamics and in information theory. But I think when people start using it informally, um, it gets a little more dicey. But I would say if Lamport is willing to invoke it, then I am willing to also.
I find his career inspiring and the things he talked about also inspirational. I appreciate being able to sit down with one of his papers and keep bashing my head against it until I understand it. And sometimes I fail, like in the Paxos paper, but I'll keep trying. And appreciate the the crystal of truth that seems to be there below the surface on a lot of these ideas that seems relevant to the work that I do as a day-to-day software engineer. What do you take out of Lamport's body of work here, Mike?
I would agree with what you said. And I think I also, as I sort of mentioned earlier, there's just some ideas that he states that are not necessarily principles of distributed systems, but they're just sort of definitions that stick in my head when I'm thinking about things now. Um, Recently we've been doing most of our stuff using a, you know, asynchronous stuff in Python, and so I've been thinking a lot about how does concurrency in the asynchronous sense conform to concurrency in the distributed system sense or the multiple thread sense. And it helps me to go back to the basic things that he was talking about in 1978 to reason through what those things are doing. And so I think there's some stuff in there. I've mentioned this to you before. I think every programmer should have a concept, should have a good idea of what partial and total orderings are.
Hmm.
I'm sure real computer science students learn that in discrete math at some point in time, but I just feel like that's one of those things that is, it's a basic mathematical idea, but I think it's important to people doing any type of programming, and especially in distributed systems.
Hmm. Set theory, too. A little bit of set theory is useful, too.
Yeah, I would think so.
All right, that's pretty good. I like that last word. This was a great topic. I hope we did an okay job covering it. There's so much material here. There's obviously a lot more than we talked about. Anything else you think? Are we missing anything that we need to raise?
I don't think we're missing anything. I guess the difficulty of talking about Lamport is, or this topic in general, is that it's difficult to talk informally about something that is pretty technical.
Hmm.
Um, so I
Yeah.
guess I would encourage people to, if anybody's listening and they find this interesting, to, look into it yourself. Um, there's a lot out there about distributed systems, a lot out there about Lamport. He's a Turing Award winner, so there's biographical information about him and sort of summaries of his work all over the internet.
That was a sweet reading rainbow ending for this here, Mike. All right. Thanks so much for talking to me about Leslie Lamport. And this has been Picture Me Coding. My name is Erik Aker, my co host, Mike Moll. We will see you again next week.
See you next time.
Bye bye.